One of the examples that we have for interference is Young's double slit experiment, which you'll be doing as a prac. So the idea behind this is that you have monochromatic light at a certain wavelength in phase, incident on two slits. And what you find is a series of dark and bright fringes on the screen. What's happening? Well, if we have a look at it in this way, our light's going through and it relies on the light diffracting through each slit. And when the light overlaps, you get interference, just like in the ripple tank. So you can see you're going to have diffraction through here. So that light travels that way and basically everywhere there. And you have an interference pattern in between those things, which will look a little bit like this. I'll show you a better interference pattern a bit later. Some of these fringes may be missing when you have a minimum, but you'll definitely have a central maximum, and then you have a maximum coming out from there. So what does it come from? Well, each slit, when a light travels from this slit here through to this point on the screen, it actually has to travel slightly further than this point. Because it's travelling slightly further, but it's travelling at the same rate, so the wave velocity is the same, it means it has a little bit longer to travel, and if you can have a look at these waves that appear, it's going to be slightly out of phase. So this wave here and this wave here are slightly out of phase, and when the waves arrive at P, you're going to get a minimum or a dark fringe. So the general condition for a minimum is when this difference between these two lengths is m plus half of a lambda. So remembering half of a lambda means that it's going to be half a wavelength out of phase, where m can be 0, 1, 2, 3. Sometimes you might see this as an n. I prefer to use m because it's not used as another constant, whereas n is. So if you've got half of a wavelength out of phase, then you're going to get a minimum or a dark fringe. What happens if the same thing happens, but instead we want to get a maximum? So the waves arrive at P in phase this time. So you can see they arrive in phase. That means that this one's travelled slightly longer, but it might now be in phase. So the condition now for a maximum is that this difference in these distances that the wave travels is an integer unit of the wavelength. So it doesn't matter if it's 1 or 2 wavelengths behind this one, as long as it's an integer unit of the wavelength, where m is 0, 1, 2, 3, 4, 5, 6, 7, whatever, then you're going to have a maximum intensity. So assuming that your sources are coherent, when your wave arrives at this central point, in this case and in this case, it's going to have the same number of wavelengths, and you're going to have a really bright fringe. That's your central maximum, and that's where your constructive interference occurs. So here's another way of looking at this double slit experiment. So the wave comes in here, you have an angle here, and you have a distance y. And what happens is that you end up with a diffraction pattern that looks a little bit like this. So you see that central maximum, and then as they interfere constructively and destructively all along there. So how do we get this condition? Well, we've kind of given it a condition saying if you've got a maximum minimum, it's going to be a integer wavelength. But there is a few assumptions that we make. One is that we have an infinite source. So we have a light source that's an infinite distance away, so that when the wave arrives at the slit, all of the waves are in phase. And the other thing we do is we say, okay, well, let's see. If we look at this angle here, theta, we can see that there's the distance theta, and here's d, which is the distance from the screen to the slit. And we can look at y, which is basically going to be the distance between, say, 2 points on this screen. And what we want to find out is, okay, what is the distance between two maxima? And how can we then relate that to the wavelength of the light, for example? So we make the assumption that for very small slit widths, this distance here is going to be so much greater than A that you can kind of just say, right, I'm going to use this distance here rather than trying to use the difference here and the difference here and the fact that you've got a very small A here. So you're going to approach it at right angle, which means you're going to be using this here. So for a distant screen, assumption your tan theta is approximately equal to sine theta, which is approximately equal to theta, which gives you the y on d. And this is how we get an expression for a maximum. We say that d, our slit width, slit distance here, times sine theta, which is approximately equal to tan theta for large distances, is going to be an integer number of wavelengths. Or if we rearrange that and say, well, you know, if we make the assumption that sine theta is closer to theta, then really we can make that assumption that theta is y on d. And then you get a description for the distance here that is only a function of the slit separation and the distance between the screen and the slit. So where on the screen will the maximum and minimum be located in terms of lambda, theta, and that, assuming d is much greater than little d. So for constructive interference, we should have d sine theta equals m lambda. We should make that m. And d sine theta is equal to m plus a half lambda for destructive interference. And that all comes from this angle assumption. The double slit experiment was actually found in 1801, which is ages ago, 200 years ago. He found that the wavelength of the sun was about 570 nanometers simply by using this experiment. And he used this two-slit experiment to prove that light is a wave and that a diffraction pattern results if the electrons, or the source that's used, if electrons are used. So you get electron diffraction patterns. Now this proved one of the things about particle wave duality, which wasn't actually proven until much later, but this whole idea of whether light was a wave or a particle comes from this description, this experiment. And you get a de Broglie relationship for the particle's momentum, which is a function of the wavelength. So a diffraction pattern can also result for a single slit. Okay. Well, it works because of a principle called Huygens principle, or maybe it's Huygens principle. I think Huygens principle sounds better. And he basically said that every point on a wavefront may be considered the source of a secondary wavelet that spread out in all directions with a speed equal to the speed of the propagation of the waves. So basically, if you have some waves coming in here and they come into a slit, then every point in that slit could be considered as a source of more waves. And you can see that these waves then fan out and you get an interference pattern. You can use a single slit and make the same assumption so that you still get that same relationship between y and lambda for a minimum, and remember for the maximum it's m plus a half, using again that angle assumption. So another principle that's kind of interesting, and what we'll probably do in about week 4 or 5, is Babinet's principle. So an object and its complement, or its negative, produce the same diffraction pattern. So if you try to get a diffraction pattern from this, it would be exactly the same as a diffraction pattern from that. And that means that even though we've been talking about slits, where you might have a very thin slit where the light goes through, you can also get a similar diffraction pattern from something that's very thin but is not a hole. For example, a hair. And that's one of our experiments a bit later. So one of the conditions that we had for this experiment was that we had coherent light and that was in phase. But our normal light sources aren't coherent. They're not in phase. They just, emit light, not necessarily all the same frequency and not all at the same amplitude. So what do we use? Lasers. Lasers are great because they emit coherent light that is in phase. So sunlight, not very much in phase, lots of different wavelengths, lots of different colours. An LED would be one colour, would be great, but the waves are not coherent, they're not in phase. But a laser brings all of that together. one of the good reasons why we're using it in our experiments. So even though we talked about slits and then we talked about hairs, we can also have a number of slits. And a number of slits are called diffraction gratings. And a simple example of diffraction grating is maybe when you look at a CD, you can see the reflection and the diffraction of light off there, and it forms a rainbow. And that is because the grooves in a CD are very, very small, similar to a diffraction grating. And so we can use that same expression that we had before, but this time we're actually using d sine theta equals m lambda, where d is, instead of being the slit separation, it's actually the grating spacing. So it's talking about those slits in the diffraction grating. And it's used to separate white light into different colours. What are the applications? Well, diffraction is useful in so many different ways. One of the ways that we use it in science is X-ray diffraction. So if we use a light source that's not, for example, a laser, then we can actually get information back from solid substances such as crystals. So X-ray diffraction is one of those things that was used initially for crystal structures, and in fact it was the technique that managed to find the structure of DNA. So it's incredibly useful, and it's commonly used these days to find the structure of new drugs and things like that. Electron diffraction is much lower energy, so you tend to get a lot more surface energy. And one of the projects that I worked on when I was a PhD student was using electron diffraction to look at the crystal structure of gold crystals, and the surface structure and thin film measurements that you might make are much more suitable for electron diffraction. If you use neutron diffraction, you can get information about the magnetic moment, which means that you can look at the magnetic structure of different materials. All of these applications